Okay, so we are going to talk about Compton and de Broglie today. We want to be able to determine the wavelength of a person. Now, you might think I've jumped the shark a little bit, but you'll see what I mean here in just a second. So first of all, Compton effect just shows that it says that an electron has energy, which is Ke. The kinetic energy is 1/2 mv squared, which you know. And an X-ray has energy. It's the E equals Planck's constant times frequency. And after the collision, due to the conservation of energy, the kinetic energy of the electron goes up and the electron of the X-ray goes down with a lower frequency. So it proved that photons do have momentum, even though it's light, and we don't really associate photons with having a mass. And the amount of momentum is proportional to the energy. The law of conservation of momentum still works on the quantum level. So it means that waves act like particles. De Broglie, it says that the momentum is equal to the energy divided by the speed of light, and the energy is Planck's constant times frequency from the photoelectric effect, and the velocity is frequency times lambda. So therefore, the speed of light is equal to the frequency times lambda, and p is the momentum, which is equal to mass times velocity. The momentum in this case is a little more complicated than mass times velocity. We have to get it through a different way. It's the energy divided by the speed of light in a vacuum, and that's equal to Planck's constant times frequency. And when we solve for that, we can find that that evens out, that goes to Planck's constant divided by lambda. So then we get the momentum is equal to Planck's constant divided by the wavelength. And the wavelength is Planck's constant divided by the momentum. And this is Planck's constant divided by mass times velocity. And this is on your reference table. We have this as, on the reference table, we say it's E is equal to HF, which is equal to HC divided by lambda. This is on the reference table here. So then the wavelength of matter is the Planck's constant divided by mass times velocity. So again, this is the E equals HF here. And then it's also equal to HC divided by lambda. So it means that matter behaves like a wave. So they will interfere and diffract depending on the size of the object. So wavelength is inversely proportional to momentum, to the mass. Everything has both a particle nature and a wave nature. Massive are more particle-like and less wave-like. Less massive are more wave and less particle-like. So here's an example. What if we had a 70-kilogram man moving 5 meters per second? What is his wavelength? This is going to be lambda is equal to h divided by mv. So then it's just 6.626 times 10 to the minus 34 joules divided by 70 times 5. And it's 1.8 times 1.89 times 10 to the negative 36 meters. This is tiny. So that's why people don't diffract. because the wavelength is just too small. And if you remember, diffraction has to happen on an opening about the same size as the wavelength, and that wavelength is just too small, and people are way, way bigger than that. So we can't diffract. Okay, so then we have lambda equals h divided by mass times velocity. Electrons have a wave property where the wavelength is about 10 to the negative 12th meters, which is about the wavelength of an X-ray. So this here is a snowflake on a TEM probably, so that's a transmission electron microscope. This is an ant, or maybe I think it's an ant. And so we can use, what this is basically saying is that we can use the wave properties of electrons so that they can diffract and interfere, and it's used for electron microscope.
The scanning electron microscope is one of the most powerful microscopes in the world. It magnifies objects up to 200,000 times. That kind of power can make an Asian tiger mosquito, for example, which is only 5 millimeters long, look like an alien creature the size of a T-Rex. At the top